Okay, in this video clip, we're going to measure the seepage velocity at two different locations in the flow model. And the purpose of this activity is to physically see the relationship between the gradient and the seepage velocity. And also, what we're gonna do is inject dye in this flow channel, and we're gonna inject dye in this flow channel. And so hopefully the dye will stay in the flow channel. That would mean we drew a decent kind of flow channel. And then we're also going to look at the relationship between the gradient and the velocity, the seepage velocity. In this case, we're going to measure the seepage velocity. So if you look on the data sheet, we're doing this seepage velocity evaluation. We're going to inject it at two locations. So the horizontal distance from the sheet pile. So we're going to inject it, so horizontal distance from the sheet pile. We're going to inject it right here, and we're going to inject it right here. And I have kind of we'll write the data down here. So that first one's 2 centimeters from the sheet pile, the other one's 8 centimeters from the sheet pile. The only reason we're even writing this down is so we can have an idea of where the dye was placed. This isn't used in any of the calculations. It's just so we know where we injected the dye. Okay, so we're gonna inject the dye. It's gonna kind of go down and stay in this flow channel. When we get to this first equal potential line, we're gonna start a timer. When the dye hits this equal potential line, we're gonna start a timer, and we're gonna measure the time it takes to travel from this equal potential line to this equal potential line. Okay, we're gonna measure that time, and then with the ruler, I'm gonna measure the distance, and that's the distance the dye traveled in that time. Of course, the distance over the time, that is the seepage velocity. Okay, for the dye that I inject over here, that's 8 centimeters away from the sheet pile. When we hit this equal potential line, we're gonna start the timer. When we get to this equal potential line, we're gonna stop the timer, we're gonna measure that distance, and we can calculate the seepage velocity over here. So, we also wanna look at the gradient, right? So the gradient is the change in head over the length that it takes for that head to change. Okay, so the change in head from here to here is 1 head loss per drop, right? So whatever the head loss for us, it's 2.5 centimeters. So the change in head from here to here is 2.5 centimeters. The distance, why don't we just measure it right now? The distance is 5 centimeters, or 4.5 centimeters, okay? So over here, the head loss to go from here to here is also 2.5 centimeters. After all, it's 1 drop, but the distance is like 6 centimeters, okay? So therefore, I'm gonna just write this down. The gradient is the change in head over the length, right? So here we have 2.5 over 4.5. Here we have 2.5 over 6. So the gradient is greater here than it is here. So where we have like really tight little figures, we have a shorter distance but the same head loss per drop, so we have a higher gradient, right? So we should expect to see a much quicker velocity where we have a greater gradient. So this, we should see the water flow much faster, you know, through here than it does in this channel. So let's have a look at that. It's not the greatest experiment because this dye kind of diffuses a bit, but you'll get the idea. And it's red. Ooh. Okay, so once the dye gets to this line, I'm going to start this timer. I guess I'll start it now. That timer will sit over here, and once the front of this die gets to that equal potential line, I'll start the other timer. It's not too exciting, but it's kind of cool. I mean, it's staying so far in the in the flow channel. I'm going to stop that first one because we're already to the second line, and this one's starting right now. Okay, so we had 36 seconds. I'll record some numbers over here. We had 36 seconds, and we traveled 4.5 centimeters. And then when we were 8 inches away, I said it was 6 centimeters travel time. And it's getting there. It's pretty slow. But we are in the flow channel for the first one, right? Yeah, we're in the flow channel. So that's awesome. I'm a little worried about this. Let's see how that goes. Okay, so we'll get this second reading, and then you guys can calculate those seepage velocities, and you can calculate the gradient, at least the gradient. Of course, the gradient's changing, right? The gradient throughout this whole system changes as the water flows through there, because anytime the length between equal potential drops is different, then the gradient's different. So this could kind of, start off slower, then it could really speed up, and then it can kind of slow down again, right? So, I better stop that. So anyway, that's 87 seconds. So let's have a look at let's make sure we get the video over here. So 87 seconds. So we traveled 4.5 centimeters in 36 seconds, 6 centimeters in 87 seconds. So you can calculate those two seepage velocities. You can calculate the gradient. Well, the gradient was the change in head over the length. That head changed. So for the first one, we went from one equal potential line to the next. So the change in head for this first location was 2.5. The length was 4.5, so you can calculate the gradient. For the other injection location, the change in head was also 2.5 centimeters, but the length was 6, so we have a lower gradient. So we should get a slower or a lower seepage velocity.